Welcome everyone to an interview with Anton Sheykin. Today we're going to talk about universal constants as manifestations of relativity. We're going to take a rather philosophical vibe in the discussion, and we're also going to focus on some historical perspectives on physics and associated concepts. I hope you enjoy the discussion. I think a good starting point to just begin discussing it would be if we start talking about the principle of relativity with respect to observational means. Maybe a little bit of historical background if you want to give that regarding the concept, and then I think most importantly just to conceptually describe what that concept relates to.
I would like to give some historical remarks because actually that principle was proposed by our founding father, Vladimir Alexandrovich Fock. It's one of the key people of the quantum mechanics. He created Fock space, Hartree-Fock method, and so on. But in his later years, he was working on interpretation of quantum mechanics and proposed this principle. But when I started to dig into the literature, I discovered that many people before Fock in the 18th century or even 16th century has actually talked about it as well. And one of the most interesting books about perceptual relativity, so to say, I saw on your channel an introduction to one of the theories of
We can
perceptual
link that
relativity.
in the description afterwards.
Yes.
Yeah.
One of the most interesting books is Plurality of Words by Fontenelle. Conversation about the plurality of worlds. It's a popular book about the physics written at the end of the 17th century by the philosopher who presented the main concepts of Newtonian physics through a conversation. And I would like to give one small quote from this book because it's very popular and I think it's very enlightening. All philosophy is founded on two things: an inquisitive mind and defective sight. Later he goes on to explain why we cannot know for sure if the sun is just one of the many suns in the universe, because the sun is very far away and we have bad sight. And actually, the question about how our means of observation can affect our physical theories was widely discussed by British empiricists, for example, Locke, Berkeley, and so on. So I think this principle can be traced back to the works of British empirical school of philosophy, and emerged in physics in works of Ernst Mach and Henri Poincaré, who made a remark about the meaning of the speed of light in one of his late papers about principle of relativity. Poincaré said that if we see the speed of light in any formulas describing gravitational interaction or electromagnetic interaction and so on, it could be because all in the world are of electromagnetic origin, or it can be possible that something in the speed of light is connected with our means of observation, and this constant just shows us the limits of our means of observation.
How do you mean when you say that it's showing the limit of the means of observation in that case? So I guess we'll come into some of the equations that tie these concepts together in a second in the paper. But could you conceptually explain why would us observing a constant speed of light be indicative of us hitting some kind of boundary with respect to our observational means? And could you also
let me try.
To preface that even more, could you maybe just explain what observational means is very simply as well, so that we're all on the same page with that?
I will try. What I mean by the limits of perception is imagine the observer that can move at the speeds of the order of the speed of light. And for that observer, the speed of light is not special at all, because it's not very small or large, and it has no special meaning. But for us, the speed of light is immensely large, and it shows us that we're actually very slow comparable to other processes in the universe in which the photons or gravitons are moving. What is the mean of perception? It's our senses, so to say, because if I could try to describe my paper in three phrases. We are very slow, very big, and can't count to the 10 in the power of 93, the Avogadro's number. And these three facts lead to the appearance of three physical constants: speed of light, Planck constant, and Boltzmann constant. They show us that we cannot directly interact with things that are very fast or very small or have a very large number of constituents.
Why do the fact of these being constant imply that? Or is that not what you're saying? So we have these constants, they're universal constants, presumably universal constants, and they have either very large or very small numbers. That's fair. Are you alluding to the size of those numbers? Is that what you're saying? Or are you saying the fact that they are universal constants to begin with is showing us the limitation?
Well, actually, the most important property of these constants is this dimension. They all have a physical dimension, and well, I'm just starting to describe my paper, yeah. And all dimensional constants can be divided by three groups. It's the classification of physical constants proposed by Jean-Marc Lévy-Leblond. He says that all physical constants which are dimensional could be the characteristics of the objects. For example, it's masses of elemental particles, their charges, or anything like that. They could be characteristics of the phenomena, I mean interaction, electromagnetic interaction, gravitational, and so on. And they can be truly universal. It means that these constants did not describe a single particle. For example, the mass of the electron describe the electron and nothing else. The charge of the electron describes electromagnetic interaction and no other interaction. But the speed of light and Planck constant describe all range of physical phenomena, and they actually synthesize together different concepts in the corresponding theory. For example, the speed of light connects the notion of space and time together. And say to us that in the relativistic theory, it's the same quantities, and we can add the time intervals to the space intervals and subtract it from each other. And for the creature that is truly relativistic, this split to the space part and time part makes no sense. And because we are not relativistic, that is the limit of our perception. We distinguish these notions, the space and time, or in the case of Planck constant, momentum and coordinate, because we do not belong to this world. This means relativistic world of or quantum world, and so on. So they are dimensional. They have dimension, and they are either very big or very small. These two properties are the most important ones.
If I can challenge this view a little bit now, so we have also these categories on the screen. So as you said, we have characteristics of objects, and then of phenomena, and universal constants. So if we say that we have some characteristics of the objects, let's say that we're considering, I don't know, the mass of some object, and you said that the universal constants synthesize our theories. So we have the synthesis using the speed of light to synthesize our, let's say, gravitational theories with our theories of time and space into one holistic framework. But you take something then, so if we look at mass in this original example, that would belong to a non-relativistic object at first, so we would classify it as a characteristic of the object here. The mass of the object would be in category A, and you're saying that C, the speed of light, would be in universal constants. Let's say we're now synthesizing this into a larger theory. We're saying relativity is now our theory. Doesn't C like C as in the speed of light fall into type A here again then? Because then you allegedly have our universe, let's say, which you could make a case for is one object of type space-time, and it has a characteristic that is the speed of light in that framework, which is C.
Well,
so how do you make this, let's say, unambiguous as to which category you assign a given variable to?
I could try to answer that, yeah. I think the main characteristic of universal constant is the following. When you put the mass of the particle or its charge or something like that to zero, the object disappears. You can talk about the particle whose mass you set to zero. If it has non-zero mass at the beginning, if you take the limit of the constant of the category A and get rid of this constant from your theory, the object disappears. The phenomenon disappears. You can talk about gravitational interaction if you took the limit g to zero. Yes, there is no gravitation if you set it to zero. But if you take the limit c to infinity, yeah, you have still some objects that are moving. You have classical mechanics. You still have a theory, but it's another theory.
Well, I guess the appropriate equivalence would be if you take it to zero, no? Like, let's say you take speed of light to zero, and you still impose the constraint that c is the fundamental upper limit of movement in our universe, or movement through space-time.
If we set the speed of light to zero, we will arrive at another case of mechanics, another case of kinematics. It's called Carroll kinematics. It was described by Lévy-Leblond also. And in this mechanics, the coordinate and time would be different again, but their roles would be somewhat swapped. What I wanted to say that the universal constants define how we are looking into things. They define what type of theory are we using. Other types of fundamental constants describes a set of objects or a set of interactions between these objects. But if you don't use these constants, there is no such objects or interactions between them. But if you don't use C, you have classical mechanics. If you have used C, you have relativistic mechanics. If you don't have K, Boltzmann constant in your theory, you have thermodynamics, for example, because in thermodynamics you have only universal gas constant, which is Boltzmann constant multiplied to Avogadro's number. But in the thermodynamics, you have an infinite number of particles, yes? If you take 1 mole of your gas, in the true thermodynamics, you cannot say how many particles are in here. It's infinite number of particles. So the Avogadro's number in true thermodynamics somewhat losing its meaning, and only the multiplication of Boltzmann constant and Avogadro's number has sense. What I'm trying to say is that, for example, you're studying some gas, yes, and you can approach to this physical system from 2 points of view. You can assume that the gas consists of the very large number of particles, and then you assign the definite energy to each of these particles, and you arrive to the statistical physics when you have a Boltzmann number. Yeah, but you have another alternative. You could say, I don't want to deal with any particles, and I don't want to have the Boltzmann constant in my theory, but the gas does not disappear. It's still here, but it's described by another theory in which the concepts of energy and temperature is not tied together by Boltzmann's constant. You see, Boltzmann's constant is how Lévy-Leblond say to this concept synthesizer. If we include this fundamental constant in our theory, it synthesizes the concepts, so we cannot make a distinction between them. And in relativistic theory, people often like to set the C to 1 and forget about it completely. Yeah. So if these concepts are already synthesized, then we don't need this constant. We know that it is here, but its value is of no importance to us. We work with relativistic or quantum objects at their level, at their language. And if you are doing quantum mechanics and you didn't interested in the interaction of a quantum system and the classical observer, you don't need to introduce the Planck constant at all, because it say to us how quantum quantities are related as the order of magnitude to classical quantities. So if we have a relativistic theory, we actually don't deal with corresponding constant. It hides within this theory.
Okay, fine. So we have these categorizations now of constants into these three categories. How does that relate to the overall emphasis of the paper? So if we're talking about relativity with respect to observational means?
Yes, this is the main idea of the paper, because this categorization belongs to Lévy-Leblond, and in fact, there was a paper written by Benoit Mandelbrot, who identified three of these constants, C, H bar, and Boltzmann constants, as constants describing uncertainty in different types of physical theories, because in addition to Heisenberg inequalities, Heisenberg uncertainty relations, there are analogous relations in the theory of information. They are called Gabor limits.
I think we have it on the screen now, right? So these ones?
Yes.
Yeah.
Well, it's somewhat purely mathematical fact that the function and its Fourier transform cannot both have a compact structure. If you have a sine, its Fourier transform would be a delta function. Yeah. If you have a function which is spread along its axis, its Fourier transform would be compact. And one could assign a physical meaning to these relations. And in my paper, I gave an example of uncertainty appearing when you're trying to describe a signal which is going to your receiver. And in the statistical physics, also we have some set of uncertainty relations They're called Boros and filter relations. But honestly, it's so much debate about the meaning of these inequalities. I mean, no one argues that they are wrong, but their interpretation is very unclear to the present moment. But Mandelbrot said that these three types of inequalities, in fact, describing the same set of properties which are shared by relativistic physics, quantum physics, and statistical physics. And the main goal of my paper is to relate the existence of such inequalities to the principle of relativity with respect to observational means, because Fock tries to justify this principle based on Heisenberg uncertainty relations. Fock said that we shouldn't really call the Heisenberg relations uncertainty relations, because it's rather the manifestation of relativity in quantum mechanics. There was a famous paper of Einstein, Podolsky, and Rosen, to which the Fock write a preface in 1936. And Fock says, Einstein said that the quantum mechanics is incomplete. It doesn't tell us all characteristics of the quantum system, but these characteristics objectively exists. And what Fock is trying to say that Einstein asks the wrong question, because if one is asking where is the quantum particle, for real, it's the same as asking what is the speed of a train, because there is no one answer. There are many answers according to many different observers. For the observer that is sitting in the train, the speed of the train is zero, because he is moving with it. But for an observer who is watching the moving train, the speed of the train have some value to it. And according to Fock, such situation occurs in quantum mechanics too, because if we are trying to measure some physical quantity related to the quantum system, it would not be absolute. It would be relative to the quantum state of the system and to the
How do you mean when you say
representation.
that? Can you sorry for interrupting. Can you please elaborate on that a little bit? So you're saying it's relative to the state of the quantum system. Any measurement is relative to the state of its corresponding system, right? Are you referring to it in a more specific way?
Yeah, let me say it again. If you are trying to measure some quantity related to the quantum system, you are putting this system to the specific set of experimental conditions, yeah, and you have created such conditions in which others values of interest cannot be measured with great accuracy. So Fox says that quantum mechanics isn't incomplete in the precise sense that the mechanics is complete, because if we can't answer the question what is the speed of the train, from it didn't follow that we cannot know the characteristics of the train. We can know this, but they will be relative to the state of the observer. And such situation occurs in quantum mechanics too, and Fock's interpretation lies in the fact that Heisenberg's uncertainty relations are setting the limit of the classical description of an object. If all the quantities related to the physical system are very large in relation to the Planck constant, we can apply a classical description in which all the quantities are absolute. They are not relative to the means of observation, because the observation didn't affect the object. But if we are dealing with the object which is very small, then we must apply the quantum mechanical description, and in this description we must choose what set of quantities we want to measure. It didn't prohibit us to measure another set, but not vice versa. Not at the same time. Let me give you a simple example.
Before we go on, can I maybe interrupt there with a question?
Yeah.
So, you're saying that if we're approaching the speed of light, let's say, we need to take relativistic effects into account, and that's fair. And if we go small enough, then we need to take quantum effects into account. That's also fair. What still seems to be the difference between these, and as far as I've understood, the point we're also trying to address with this argumentation now is the occurrence of the non-deterministic effects that are associated with quantum measurements. Fine, you can make the comparison and say that in quantum mechanics you have a similar situation to the train, in that you need to measure something relative to your observational means. That's fine, but you still encounter the issue of the measurement being non-deterministic, right? Like even if it's fine, you have to introduce some form of relativity to the observer. How does that explain the occurrence of the probabilities associated with quantum mechanics?
You stabbed me in the heart, because it didn't. At the end of my paper, I wrote about it a little. In fact, Fock's interpretation of quantum mechanics is very limited, and he didn't deal with the indeterministic phenomena at all. And for the people who are working in the quantum mechanics, his interpretation was somewhat useless. And the simple answer to your question, it didn't explain the most interesting things in quantum mechanics. For that specific reason, I wanted to widen the area of applicability of this principle to search for another fields in which similar situation can occur. Because in quantum mechanics, we can't do anything much with this principle. The most interesting things lies beyond the scope of it.
Mm-hmm.
So, in fact, Fogg himself say that his principle could have very broad significance and possibly can be applied to any field in which the similar situation occurs. And in my paper, I was trying to determine what conditions needs to be satisfied in a theory for it to be the object of principal relativity of, with respect to observational means. Little example, as I promised. Viktor Frankl, the famous psychiatrist, liked to present the example of the cylinder, which can be viewed from different perspectives. If you look at the cylinder from the top, it has a shape of the circle. Yeah.
Yep.
If you look from the cylinder to the cylinder at the side, it looks like a rectangle. And there is an analogy with very dumb thing, actually, which is still present in some textbooks on quantum mechanics, the wave corpuscular duality. Yeah. Some high school teachers still like to say that the electron is a wave and it is a particle. But if we apply this logic to the situation with the cylinder, we would have saved a very stupid thing. One cannot say the cylinder is a circle and a rectangle. It's simply wrong. A cylinder has a characteristics that the circle and the rectangle do not possess. It's a volume, and the main criteria for the appearance of the principle of relativity with respect to observational means is the presence of incomparability of the object under study with the observer. And such situation occurs, of course, in quantum mechanics, but it occurs as well as in the wave processes when we are dealing with the objects which are moving with the speed of light. And it occurs in statistical physics. And for the last 2 years, I've been searching for theories or phenomena that have the same property, incomparability of the observer and the object of observation. One small example. An art gallery, yeah? You look at the painting, and you ask the museum worker, what is depicted on it? And she give you an answer, and you walk away. And when the different person approach the painting and asks her what is depicted, she might give a different answer. Yeah. But if one approaches the painting and asks what really is depicted on it, she would have take a very large table from her pocket and said, this pixel has the RGB numbers and the other pixel on this painting has that, and so on. Yeah. So in fact, the quantum mechanics, it's like this picture, because we can describe quantum object fully by its wave function, but it's very inhuman way to describe in an object. To describe it in our language, we have to relate it to the classical objects, and then you will be able to say something about it. And what
So
I'm trying to say in my paper is objects in relativistic physics, statistical physics, and quantum mechanics can be described without any uncertainties, but in a language which didn't have to do with our classical quantities. The cylinder cannot be described on a language of planimetry. Yeah, it's a stereometric quantity. It has different characteristics which flat figures didn't have, and it's possible that there are other theories in which we have the same incomparability between the observer and object under study, in which such
okay. So if I can follow up on what you just said. So with these examples, it seems like you have two different ways of looking at this. It seems that in the cylinder example, you're alluding to something of, let's say, higher dimensionality, that in the process of measurement or observation is kind of squeezed into a lower dimensional representation. And then we say the lower dimensional representation is actually the thing. So we confuse the thing with the lower dimensional representation of it. That's one way of saying it. The other thing it seemed like you were alluding to is that the language, let's say, of quantum mechanics is fundamentally different, and that it somehow is naturally a language of probabilities. Those two are quite different claims, like that you would either have something in a that objects on the quantum scale, or all objects, maybe for that matter, would be much higher dimensional than we give them credit for, let's say, and that the process of conducting a measurement is sort of squeezing it into a mold that it's not necessarily built to squeeze into, or that doesn't do it full justice, let's say. Or are you saying simply that the language that we're using is not really compatible with the language that inherently that these objects inherently communicate with?
Well, Fox's point and my point as well is the following. When we are saying the flat figures, circle and rectangle is a thing, we say it as if we were creatures of flatland. Yeah, if we are crawling at the walls of this room in which the cylinder is present, and for these creatures, it's a thing. And because we are, as I said earlier, very big, very slow, and consist of many particles, for us, the language of observables, classical observables, is the thing. And it's obviously incompatible with the language of fully quantum description of quantum object by density matrix or wave function or whatever, because in quantum mechanics, for example, you have complex valued functions. Wave function is complex valued, and in classical physics, there is no analog to it. You simply cannot assign this property to any classical quantity. Well, I hope you answered your question. No?
Well, I guess another perspective of looking at it as well would be, if you take the cylinder example, the problem is kind of not so much with the object being incompatible with having questions asked about it, but more incompatible with the specific type of question you're asking. You're asking not what is this object, but you're asking what is this object seen through the lens of two dimensions.
Exactly.
And are you then alluding to that, like a way of extending that analogy would be to say that in fact there would be measurements we could make on quantum objects that actually preserve the state of the quantum object, that doesn't cause it to collapse into one of these states, but that we just don't know the measurement yet. Is that is that a trajectory you're pushing for as well, or is that simply another consideration on my part?
Well, it's very optimistic way to saying this, because you assume that someday we will find it, but I'm not so convinced, because I believe that we are somewhat bounded to our means of observations related to our bodies or our society or so on. So, in fact, there are answers, there are questions which I'm afraid can be answered. And the question, what is really a quantum mechanical object? It's one of such questions, I think.
I mean, I guess the optimistic way of looking at that question is there needs to be some causal relationship between the objects that are associated in that event. Like, let's say you're measuring a quantum object. You're obviously impacting the object in some way. There is some causal relationship between them because your outcome is determined by that measurement process. And so we might not have it in our human senses, let's say, to grasp all the things that are associated with a quantum object. Obviously, we don't, given the scales that these operate at, but potentially you could make the case that given that all of this is causal, having a fully causal representation of your object, or only representing the parts of the object that could have causal influence on other things in the universe, would be sufficient. And I mean, I'm not trying to make a case for either or, but I'm just saying, I don't know. I'm just saying there's to me, it doesn't strike me as impossible that there would be, like, following that line of argumentation, a way to measure something like that in another frame of reference, let's say, that takes more into account, that doesn't collapse the state.
It could be possible that one can imagine a way to interact with the quantum system in such way that we are preserving these quantum properties, and we didn't want its wave function to collapse. But I'm afraid that if you try to describe such way in the language of coordinates, momentum, energy, time, and so on, you will not succeed, because
I mean, so I agree with you. There are many things I'm leaving out, right? Like, if you measure a system, you don't revert to the quantum state afterwards and do a new measurement on it. Like, you collapse the state. So yes. I'm not saying that's a viable approach, but I'm just saying in the context of that analogy, that's a way you could pursue it. But I see that we're running up on time. We have like 5 minutes left. So would you mind, just given what we've discussed now, if you want to summarize the paper a little bit on the key points that you would like to highlight that you haven't discussed yet?
Yeah, okay. In summary, the key ideas of my paper is the following. The description of the objects in physics depends on the type of these objects. If they are comparable to us, we can describe them in our language, and some very large and very small quantities like speed of light and Planck constant didn't appear at all. But if we are working with very small quantities, very fast objects, or the systems with many particles, we are forced to invent the way of representing the state of such system, and due to the incomparability of such systems and our perception, the fundamental constants, truly universal constant appears, which are describes to us how exactly big we are in comparison to such systems, how slow and how many particles are in us. And this constants leads to the phenomena that could be perceived as uncertainty, but in fact it's merely a relativity with respect to the way we are looking into such inhumane systems. And this situation occurs in many areas of physics, and I believe, according to Fock, in many other areas of science as well. So if any of our listeners have any ideas, I'd be very glad to discuss them.
Okay, awesome. Thank you very much for the summary. Before closing, are there any other points that you would like to raise? Like any other things you want to highlight?
Give me a second. I would like to speculate a bit about what fields of science can it be, because I hope that I will find somebody to discuss with. I believe that the similar situation could occur in the sociology in particular, because there is the description of the single person, and if we want to, if we are trying to describe the whole society in such terms, we will fail, and we need to invent the inhumane way to treat the system of individuals and describe it in the different language. So sociological questions, maybe linguistics, maybe finance, your area of work. Maybe in these areas we have similar situation. Let's discuss.
Mm-hmm. Okay, awesome. Thank you very much, Anton, for taking the time to join. I enjoyed the discussion a lot.